Hey everybody, this is going to be our final video where we kind of wrap things up. We're going to start talking about something called the natural exponential function, and we have to define this thing a little bit first, okay? All right, the first thing I'm going to talk about here is another formula for compound interest. If you don't know what compound interest is, if you haven't heard of it before, and you probably have in your Math 1 class, what happens is if someone's going to pay you, say, 5% interest in a year on a deposit you make or some initial investment, that means after a year, they're going to give you your principal plus 5% on top of that, right? Okay, if it's going to be compounded, all right, it says is the addition of interest to the principal sum of the loan or deposit. It's the result of reinvesting the interest. Okay, so what would happen is if I was going to say I'll pay you your interest halfway through the loan, add it back, not loan, halfway through the term of the 1 year, add it back, and then pay the 5% of that sum. So in other words, that's what they call compounding. Rather than paying it out, so the interest in the next period is then earned on the principal sum plus previously accumulated interest. This sounds really confusing in that little paragraph, but it's really not that complicated. But then you got to think about this is happening within a year. So you can compound it multiple times per year. You could compound it like 12 times for monthly, 52 for weekly, and so on. All right, so here's the formula we have for this. It says compound interest formula. Compound interest is calculated using the same type of formula we just saw up top. And what we notice here, we got the A of t is the amount after t years. You got your principal, which is your initial amount or investment. Rate's the same thing. N's the only difference here. N's the number of times interest is compounded per year. Now notice this. If n is 1, it's just your normal interest, your normal formula. 1 plus r to the t. All right. So I put an example down here. I said, well, for example, someone invested $1,000 at a rate of 5%, and maybe it's for 10 years, compounded semi-annually. If you see semi-annually, they're talking about n being 2. Right? And we know t is 10 because that's your years. Your rate is 0.05. Your 5%, and your initial investment is 1,000. So let me just show you how this looks in calculation terms. All right, so this would be without compounding. You'd have $1,628.89 after 10 years if you invested 1,000 at this rate. Okay? Now, suppose they're going to compound it semi-annually for you. That means 2 times we would get an extra, not quite even $10, right? It goes up by about $10. And here's what I wanted to show you. If we took this number and we said, what if we wanted to compound it more than that? Let's say we're going to compound it, say, every month, right? Then that would become a 12. And this would become 12 times 10, right? And you get about another $9 or so. But you can tell as I increase the compounding interval, I'm compounding it more times, the amount does go up. All right, but I wanted to show you a graph of this that I've kind of toyed around with here in Desmos. And what this is, to be clear with you, all right, this is the same thing we just looked at. $1,000 invested. The rate is 5% for 10 years. Only this time I made my variable just because I wanted to show you something. The compounding terms. In other words, my variable is the number of times I'm compounding it. So I'm going to look at the amount as the compounding changes. So if I look at after 2 years, there's that 1638, right? And there's our x-axis down here. And this is if I compounded monthly. There's that 1647 we saw. And what I wanted to show you is what if I compounded it, say, I don't know. Remember that 1647 number. What if I compounded it every, say, I don't know, every every week. That's 52, right? Now go out here as close as I can get to 52. It's not going to be a big difference here. 1648. So we're sort of reaching a plateau here, aren't we? We started off going up really quickly, and now we're looking at, after 2 we're at 1638, and then 12 we're at 1647, and if I do it every week, I'm at 1648, and I could say, what would happen if I did it every day? I'll set my window to 370. And this will get me really close. Not much difference at all. See that? I'm looking at the y-coordinate, by the way. And what you're seeing here is it doesn't change much at all. Now, what's happening is there's a horizontal asymptote here. In other words, this expression reaches a horizontal asymptote. And the key expression here, that 1,000 is just a multiple right out front of it. It's what's raised that y-intercept up to 1,000, and it grows from there, right? But this thing right here is what's causing this asymptote to happen. And that's the definition of your natural exponential function. So I'm going to go back to the notes, and I just wanted to show you that phenomena happening. Just to be really clear, as the compounding interval increases, as it gets large, this thing approaches some fixed asymptote it does not go beyond. Okay? Now, that's where the notion of the natural exponential function comes from. This is the bare definition. Don't get carried away with this looking really complicated. It's going to get very simple very soon. But I just got to show you a few things first. All right, the natural exponential function. There's a number, a lot like pi. It's the number, it's a lowercase letter e, and it's not to be confused with variables. It is not a variable. It's defined as the value that 1 plus 1 over n to the n, that's that expression you just saw me messing with, approaches as n gets large. In other words, if we define the function f of n, kind of like what we just looked at, 1 plus 1 over n to the n, what happens is as n goes to infinity, that's this number here increasing, like we just saw with our little example of the interest problem. F of n, that's the output value, approach e. So it's coming to a fixed number. Ours was coming to the fixed number of 1648-ish, something like that, right? Well, this expression approaches e. And there's that same expression we saw in the compounding interest. And this happens frequently in exponential behavior. And they gave it a name. It happened so frequently, they said, look, we're just going to call this phenomena the number e. Okay? If you want to know what e is, it's kind of like pi. Pi is actually a number, although we represent it with a letter because we don't want to carry out all those places. Okay? So here's what happens with this expression. Watch. If n is 1, you get 2. N is 5, and then we're going up in big chunks here. You get 2.48. 10, you get 2.59, and so on. And notice it reaches this 2.7, and it starts to, I call it plane off, but it starts to plateau off, right? And it's reaching that horizontal asymptote that we see in this language here. And I have carried this out. The approximate value to 20 decimal places of e is right here. So e is actually a number. When you see it in a problem, don't overcomplicate your thinking and think you've got some other variable to deal with. You don't. All right, so let me show you on your calculator where e lives. If you ever want to, if you ever forget what value it is, because you're not supposed to memorize 20 decimal places. Your calculator has it memorized for you. Second, the divide button is where e is, okay? And it gives you its value. It carries out a few places for you. I always remember it as about 2.718. Although I don't use it that way because my calculator has it stored with a whole lot more accuracy this way, okay? There's also e to the x right here. You want to raise it to a variable, an exponent. It's so frequently used, guys, this calculator is built in with this language, okay? Of e. That's like if you say, well, what's the value of pi? Well, your calculator has a pi key. And you guys need to be using that unless otherwise specified, right? You need to use your pi key unless they tell you approximate using 3.14. Here, we're going to use the e key as much as we can, okay? So that's what e is. Let's roll down here and look at the exponential function really quick. It says here the natural exponential function. is an exponential function f of x equals e to the x. Now don't get this overly complicated. Like we said, this is just a number. That's not two variables you're looking at. This is a function of only x. That's that little number we saw a minute ago. It has base e and is often referred to as the exponential function. All right, what we're going to see is if someone says, here's where this thing comes up, and we'll get to problems like this in another video. Here's one we'll run into that you don't have in a problem set right now. Let's write our function down. F of x equals e to the x. There's another formula we're going to find. Well, let's call it a of t. Sorry. It looks like this. A of t equals p e to the rt. And this is the principal, rate, and this is the rate, and this is time again. And what this is called is continuously compounding. And that means it compounds every instant. But we saw just a minute ago when we compounded that stuff with the $1,000 investment, and we started compounding 52 times, 365 times. We're talking every year. It almost reached that asymptote in 365 iterations, right? But this E says, hey, we've done it. It's done every instant. So they call this continuously compounded. So when you see the word continuously compounded, it'll be this guy. Continuous. Now, you will run into this in other problems later. This is your guy. I'll introduce it formally in the notes when we run into it, okay? But for now, that's where this leads to, and it leads to a whole lot of other formulas, okay? Anyway, thanks for watching this. I know this got long. I tried to explain it the best I could. We're going to be using this E a lot, and I don't want a bunch of mystery around it. It's just a number. But thanks for watching, and I will see you in 6.2.